Hey, hello everyone. Welcome to the Topos Institute Colloquium. Today we're very happy to have Nicola Gambino talking about monoidal bicategories and differential logic and analytic functors. So go ahead, Nicola.
Thank you very much, David, and thanks also to the Topos Institute for the invitation to give this lecture. So as the title says, I'll be speaking about three different things that have quite different origins. The theory of monoidal bicategories belongs to part of category theory that might be called low-dimensional category theory. That involves bicategories, double categories, and structures of that kind. The other is a topic in logic, which builds on linear logic as discovered by Girard, called differential linear logic, introduced by Erard and Ranier about 20 years ago. And the last is the theory of analytic functors, introduced originally by André Joyal in the context of combinatorics. And we'll see in the talk these ideas coming together. And this is joint work with Marcelo Fiora and Martin Hyland, and there's a paper on arXiv. If you are one of people like me who likes to print out papers, very old-fashioned way, wait until tomorrow because we just uploaded a new version which fixes a few typos. So don't print it yet. Okay, so it's not the first time I give this talk. Last week, I was in a much sunnier place than Manchester at a conference in the south of France. You can see a nice picture of the Calanque near Lumini. It's a conference to celebrate the 20 years of the differential lambda calculus and differential linear logic. And there's a website where you can find a lot of interesting material related to this, in particular around differential categories, which I will touch upon later, as well as the logical aspects of the theory, of course. Right. So as the title kind of gives away, this seminar will be in three parts. The first part, which will occupy most of the time, will be about monoidal bicategories. And my hope there is to persuade you that the topic is not as scary as you might think. There's a well-developed theory which can be used, greatly aided by the proof of several strictification theorems. So I'll go and revise those. And then I'll touch upon differential linear logic and describe our bicategorical setup for modeling differential linear logic. And the final part of the talk will be an example, a worked out example of a particular bicategory that supports this differentiation, and in particular will be able to differentiate generalized analytic functors, extending the work of Joyal. So at any point, feel free to interrupt me and ask questions. I'm happy to do so. Okay. So let's start off, but maybe with some motivation for doing this, coming from the interplay between logic and category theory, a very well-established topic. So on one hand, we have logic, where, for example, the notion of a formula through the Curry, Howard, Lambeck, Scott paradigm corrects to objects in a category. A sequent, gamma entails A, if you wish, becomes proof relevant in category theory. This is modeled by an arrow from the interpretation of gamma to the interpretation of A. But in category theory, we have more than just objects and arrows. We also have diagrams that express equations between arrows. And these correspond to things that in logic are called cut elimination rules. So don't worry if you don't not familiar with this. The idea, as exemplified in this example here on the left-hand side, is that there's a rule in logic called the cut rule that corresponds to composition of maps. And here's an example. So doesn't matter what some of these symbols mean, but here I have gamma entails exclamation mark A, exclamation mark A entails B, and so I can compose these two proofs and get a new proof that gamma entails B. And I've done this by cutting this formula, exclamation mark A. But I've been a bit daft here because I could have moved my cut and eliminated a formula of lower logical complexity. I could have avoided this step and just composed the proofs that gamma entails A and that A entails B to get a proof that gamma entails B, okay? So cut elimination is a process that tends to, as we say, eliminate cuts or reduce the complexity of the formulas to which cuts are applied. And as I said, this corresponds in category theory, in this particular example, to this commutative diagram, where here I'm composing D bar and D to get an identity. That's one of the axioms that plays a role in this theory. And then here I have just A, identity B, so there's not much going on here, okay, except unitality of composition. But there's something, a slight mismatch between the two sides. On the left-hand side, you see a wiggly arrow. That's because logicians think of cut elimination not an equation between two different derivations, but rather as a process that transforms a proof or a derivation into another. And that's what this bi-category theory can help us to model, because now we also have not just objects and maps, but also two cells between maps. And now we can model this cut elimination process by saying that we have two cells fitting in a diagram like this. And now we see that the process of transforming this proof into this proof is the process of transforming this composite into this composite using these two cells. Okay, so that's the general idea. We use bi-category theory to model something that is interesting in logic, namely the cut elimination rules. And now there's something extra happening, that in bidimensional or two-dimensional category theory, we also have equations between two cells. And these on the side of logic will become equations between different ways of rewriting a proof. Okay. And I'll give you an example of this type of situation a little later, okay? So this is the general motivation. Instead, let's get started with monoidal bicategories. And what I'm driving towards is some kind of bicategorical version of models of linear logic. Okay. So in the one-dimensional context, a model of linear logic or fragments of linear logic consist of symmetric monoidal categories equipped with comonads that have additional properties, usually encapsulated in the notion of a linear exponential comonad. Okay, so we're interested in the two-dimensional version of these. So what I'm going to do in the next few slides is take each of these words, category, monoidal, symmetric, comonad, linear exponential, and tell you what the two-dimensional counterpart is, okay? At the beginning, I'll go a bit more quickly because this is the Topos Institute. I expect most people to be familiar with the basics, at least, of two-dimensional category theory, but I want everyone to be on the same page, at least regarding notation and terminology. So we start from scratch, and let me just say briefly what I mean by a bicategory. Well, it's something a bit like a category. We have objects, but instead of home sets, we have home categories. And the objects of these home categories are my arrows of the bicategory, and the maps in the home categories are my two cells of the bicategory, K. And then we have composition functors, identity maps, and then the only subtle thing, which is important to capture examples, is that associativity and unitality now hold, not strictly, but up to isomorphisms, which are then required to satisfy some coherence conditions, okay? And we have a two-category when these three isomorphisms are actually equalities, in which case the coherences disappear. And if you haven't seen these coherences before, you should imagine something like the coherence axioms for associativity and unitality in a monoidal category. In fact, a monoidal category, we see in a second, is just an example of this situation. But let me give you instead another example, which will be important for our applications, namely the bicategory of profunctors or distributors or bimodules. So this is a bicategory whose objects are small categories, A, B, C, so on. And then the home category from A to B is the functor category from B op times A to set. Okay. So one way to think about these guys, an F from B op times A to set, is as some kind of relation on steroids. A relation between A and B only tells you a truth value, whether A is related to B or not. But profunctor gives you the set of ways in which A and B are related, or the set of proofs that A is related to B. Okay, these are some possible intuitions. And then composition is again very similar to the way you compose relations, except that the existential quantification is now replaced by this coend, which is taken over B. Okay, so C and A are related by G composed with F if there exists a B such that C is related to B via G and B is related to A via F. Okay, that's the way to read this, but everything is proof relevant, and therefore we're taking a certain co-limits of a family of sets. And then the identity is just a home functor for a given small category A. So this is a genuine bicategory. Composition is associative and unital only up to coherent isomorphism, okay? And this is an important example because part of the motivation would be to generalize the well-known relational model of linear logic, and profunctors will be our counterpart of relations. Another example, which I briefly alluded to before, is that every monoidal category can be viewed as a bicategory, namely a bicategory with a single object. And then the maps between that object to itself are the objects of the monoidal category, composition is the tensor product of the monoidal category, and the identity is the unit. So in fact, this provides even a way to define what is a monoidal category. It's just a bicategory with a single object. And just like there is a strictification theorem for monoidal categories, asserting that every monoidal category is equivalent to a strict one, there is a strictification theorem for bicategories, asserting that every bicategory is equivalent to a two-category, which helps to avoid, in some calculations, dealing with all these coherencies that are part of the definition. And we're going to see other strictification theorems for various kinds of structured bicategories in the next few slides. So I told you that a monoidal category can be defined as a bicategory with a single object. So what is a monoidal bicategory? Well, it's just a tricategory with a single object. Okay. And now I'm kind of heavily relying on the notion of a tricategory, which of course I'm not expecting you to be familiar with. It's a complex definition, but in fact, we won't need it. We won't need to introduce it because there's a strictification theorem also for tricategories, which in particular gives a strictification theorem for monoidal bicategories. This is due to Gordon, Power, and Street, and refined by Gursky. And the theorem asserts that every monoidal bicategory is equivalent as a monoidal bicategory to what is called a gray monoid. So we're not as lucky as in the one-dimensional case. In the one-dimensional case, every monoidal category is equivalent to a strict one, completely strict, associativity, unitality on the nose. In a gray monoid, almost everything is strict, but not quite. There's one thing that is not strict, and it's the functoriality of the tensor product. So what is a gray monoid? It's, first of all, it's a two-category, K, equipped with a pseudo-functor in two variables, the tensor, which, however, is in some sense a bit more strict than a general pseudo-functor. And then it has a unit, I, it's fine. But then the associativity and unitality are completely strict. And this is a very significant simplification over the notion of a monoidal bicategory, which is way more complex. And these type of theorems are essential for our development to make it possible to work with these structures, okay, at least up to equivalence. So next, so remember what my goal is. My goal is to define the analogs of these concepts in the theory of models of linear logic. So next, I need to tell you about symmetry. So again, let's go back to the one-dimensional case. In the one-dimensional case, monoidal categories can be, first of all, equipped with a braiding. That's a family of maps R from A tensor B to B tensor A, satisfying two axioms. And then we have a symmetry by merely requiring an additional property of the braiding, namely the commutativity of this diagram. But in two-dimensional category theory, obviously we're not satisfied with this. All our diagrams commute up to something. Oops, press the wrong button. Can you see me now? Commute up to something. So in 2D, now I have a gray monoid. That's the setting I want to work in for simplicity.
Nicola, we are
Yeah.
not seeing what you're drawing now.
I do. I see what you're drawing. You wrote gray monoid.
Oh, yeah?
Yeah.
Sorry. Okay.
Yeah.
Yes, sorry, my bad.
Okay. So I was just saying that the C in 2D is now assumed to be a gray monoid. And now to have a braiding on a gray monoid is to have invertible two cells like so, satisfying coherence conditions. But then there's something intermediate between braiding and symmetry, which appears only in this two-dimensional setting. It's what are called syleptic monoidal structures. And now we ask for an invertible two-cell there. So in the 1D case, we move from braiding to symmetry just by asking for a property to hold. Now we move from braiding to synapses by asking for more data and axioms. And then we get to symmetry again by asking for a property to hold. So let me move this. And there is a third layer. Symmetry is now an additional property, which is the coherence conditions for the synapses. Which assert that these two pasting diagrams involving the braiding and the synapses, are equal. You can kind of guess what's going on. I'm putting the synapses on either side. And I'm asking this to be equal, except that I made a typo. This should be B, tensor A. Identity, braiding, braiding. Okay? So this is what one calls a symmetric gray monoid, and it's the natural counterpart of a symmetric strict monoidal category. Okay? There's obviously coherence conditions, which obviously I don't have time to get into. I'll provide some references as we go along. And the important theorem due to Gursky and Osorno is that every symmetric monoidal bicategory, which is something very complicated to write, is equivalent in the suitable sense to a symmetric gray monoid. Okay? So, and in fact, symmetric gray monoid has additional strictness. It's not just a symmetry in the sense that I described before, but has some additional equations that simplify also the presentation. Okay, so we have these definitions, and now I'm just going to boldly claim, without giving too many details, that there is a theory of monoidal bicategories. We have notions of lax monoidal functor, of symmetric lax monoidal functor, braided, and so on. You have a notion of pseudomonoids inside the monoidal category. You have theorems asserting that lax monoidal functors preserve the pseudomonoids. It works, but it's much harder it would be much harder to develop without these strictification theorems. Okay, really simplify the way. So there's many people who contributed to this development. The story is quite troubled. It started off with papers of Kapranov and Vovodsky, which were incomplete in some ways. Baez and Neukel addressed some of the missing coherence axioms more recently, but it's not probably a very recent paper. There's a paper by Day and Street, which provides a full account of a lot of the definitions and key results on monoidal bicategories. Okay. And once you have all this at disposal, you are now ready to define what we mean by a linear exponential pseudo-comonad, because all the ingredients are part of the theory of monoidal bicategories, which we can use freely. So what is a linear exponential pseudo-comonad for us on a symmetric gray monoid? Well, we take one of the definitions. For us, it was convenient to work with one introduced by Martin Hyland and Andreas Schalk, which runs as follows. So a linear exponential pseudo-comonad on K consists of, first of all, a pseudo-comonad on K. So I write the endo pseudo-functor on K as an exclamation mark, because it's the notation used in linear logic. I have a co-multiplication, which I'm going to write P, and I have a co-unit, which I'm going to write D. And these are called P and D because they correspond to the promotion and dereliction deduction rules of linear logic. And we ask for this pseudomonad to be a symmetric Lax monoidal pseudomonad. So this means that it preserves, in a Lax sense, the tensor product. Okay, just like in the 1D case, except using these two-dimensional definitions. And then we ask for this bit. We ask that every, let me just say, coalgebra A for the comonad is in 1D, I would say a commutative monoid. Okay, here we need to be a bit more sophisticated. We say symmetric pseudo-comonoid. It's the up to isomorphism notion of commutative monoid. Okay. Well, it's a commutative monoid in the category of Eilenberg-Moore coalgebras, and I will say in a minute that this admits a monoidal structure. Okay. And then one needs to ask some requirements. So the co-multiplication of these comonoids needs to be a braided monoidal transformation. Similarly, the co-unit needs to be a braided monoidal transformation. And because these comonoids are up to isomorphism, they come with witnesses for associativity and unitality. These are invertible two cells. And we ask that these are now part of monoidal modifications. So, of course, I'm not expecting you to take in all in. I'm just showing you that on the basis of the theory of monoidal categories, such a definition can be given. Exactly as in the 1D case. Okay. For the experts, I see Valeria in the audience. So for the experts, in the 1D case, people sometimes ask for this commutative monoid structure just on the free coalgebras, but then it's a fact that it's equivalent to asking it on every coalgebra. And we expect that a similar fact holds in our 2D case, but for simplicity, we just ask for this structure of comonoid on every object, on every coalgebra.
May I ask a question?
Of course, yeah.
Are you also asking that every map of pseudo-coalgebra is actually also a map of symmetric pseudo-comonoid?
Yes.
Okay.
So one can say this in various ways. One can say this by asking the pseudo-coalgebra structures here to be natural with respect to the algebra to give pseudo-comonoid morphisms. Yeah.
So maybe I don't know. One way to maybe understand this structure is that the category of pseudo coalgebra of the bang operation
Yeah.
is actually a category with coproduct.
Yes.
Is that correct?
Yes.
Somehow that this diagonal is just will become the diagonal in the coproduct of A with A, or the product, I'm sorry, product, not coproduct, but is the category
Yeah.
with Cartesian product.
Yeah. So we're
okay.
yeah. So one way to say, well, let me just move to the next slide where I can expand and confirm what Andrea anticipated, is that assuming the pseudo-comonad just to be symmetric Lax monoidal, its category of two category of pseudo-coalgebras becomes symmetric monoidal. And then asking every object to carry this comonoid structure is asking for the tensor product to become a Cartesian product.
Okay.
Yeah. So this is what part of this theorem is, that if now we have not just a symmetric Lax monoidal pseudo-comonad, but actually the full definition of a linear exponential, then the tensor product on the pseudo-coalgebras becomes product.
What I find, I'm puzzled because if a category is Cartesian, the Cartesian structure is canonical. I mean, there's no need to put any. It's a conditions on a category.
Yeah.
And therefore one may suspect that this extra structure is actually a property of the bang comonad. It's not an extra structure on it. I mean, in the sense that if this whole structure exists and these things become Cartesian, then actually this is Cartesian in a unique way. It's just that the category of coalgebra of the bang comonad is Cartesian, which is a condition on this category, not on the structure on that category.
Yes. Well, there's something that is definitely part of the structure, I guess, is the Lax monoidal structure, because that will
Okay.
that will determine how the Eilenberg coalgebras have a
right.
product.
You're right. I think I was neglecting something, which is that this Cartesian product happens to be the tensor product, which is an extra condition. I mean, okay, fine. Okay.
There's a question, David?
No, I'm good. Thank you.
Okay. Okay, so I mentioned here a theorem proved by Adrian Miranda, who's working with me in Manchester, which is what kind of the first step you can take in developing this theory of models of one of the first steps you can take of developing this theory of models of linear logic. For the experts, there's a bit of subtlety, because even if you start with a symmetric gray monoid, what you get back is not quite as strict, but let's leave that aside. Something else that you can prove, as I mentioned before, is now that the tensor product on the coalgebras becomes a product. And something else that one can prove, again in analogy with the one-dimensional case, is that if my gray monoid now has finite products, written with this notation for the product and the terminal object, the endofunctor of the comonad becomes a strong monoidal pseudofunctor between the product and the tensor. If you unfold what this means, it's the well-known Seeley equivalencies that follow from having a linear exponential comonad. One subtlety, perhaps, is that the definition of this guy is quite involved, and a brute force approach simply does not work. So in the paper, we take an approach guided by certain universal properties to address the coherence issues. Okay. So these are just two samples of the kind of theorems that one can try and imitate from the 1D case in this two-dimensional setting. So before I promised you an example of how rewriting of proofs corresponds to coherence conditions. So here's one. So as a first step, I write now my comonad in Kleisli form. So in terms of an operation that takes an arrow from, of course, A to B, now I'm starting to call this bang or exclamation mark, of course. So I have an arrow from, of course, A to B, and I have its Kleisli extension, F star, from, of course, A to, of course, B. And now it's the fact that we have a pseudo comonad rather than a strict one means that we have invertible two cells like so, corresponding to the Kleisli version of a comonad. Okay. And one of the coherence axioms for a pseudo-comonad written in this style tells me that if I have F star and a co-unit starred, well, I can reduce to F star in two possible ways, either using this first green invertible two cell, instantiated where G is the co-unit, and then using the star of the two cell in there. And I'm simplifying this composite to F star. But I could have done something a bit smarter, because one of my axioms tells me that the extension, the Kleisli extension of the co-unit is isomorphic to the identity. And so I could have canceled this already. And one of the coherence axioms for the comonad tells me that these two things are equal. And now here's the proof theory version of this. I have one sequent, one derivation of a sequent that of course A entails of course B. And it's obtained under the assumption that I know that of course A entails B. And here I've done the cut on of course B. And I can simplify this proof, removing the cut, in two possible ways. I won't get into the details for time, but they correspond exactly to the two cells that we had before. Okay, and the coherence axiom corresponds to the fact that there is an equation between these two rewrites of proofs. Right. So this was the longest part of the talk. I want to say something briefly about differential linear logic. I assume that perhaps you've seen talks or seen papers on differential categories by Robin Cockett, Rick Bluth, Robert Seeley, or J.S. LeMay. Many others are working on this topic. So you will probably know that one way of axiomatizing differential categories, at least in a good context, is via what is called a co-dereliction natural transformation. So we're in the context of a symmetric gray monoid with a linear exponential. And now we want a version of this co-dereliction which has the direction opposite to that of the co-unit. And in good cases, which I won't go into, this guy allows us to define the derivative of a Kleisli map. The derivative of a Kleisli map, which is some kind of nonlinear map, is a map in two variables, which is linear in one and nonlinear in the other. That's the setup of differential categories. Okay. And now we want to introduce a version of this. And one challenge is how to impose coherence conditions, right? Because we can copy the diagrams, but then what coherence conditions are we to impose on these? And we found a way around this. So we work in a setting where we assume that the co-unit of the comonad, we are in a two category or a bicategory, has always a left adjoint. Okay, that's one of our standing assumptions, which is this D bar. And because D bar is left adjoint to D, there is a unit from the identity to the composite of the left with the right adjoint. But note that this need not be invertible. And then one of the theorems in the paper is that under the assumptions in this black box, there are two cells fitting in the two other diagrams that define what is a co-dereliction in the one-dimensional case. And these are constructed canonically from the structure that is given from this black box and this guy, okay? And this now provides a way to define what we mean by a co-dereliction in our setting. It's simply pseudo-natural transformations with components D bar, which are adjoint to D, such that these two cells, eta, sigma, and mu of the previous slide, are invertible. And this is one way to address the coherence issue, because, for example, take the notion of a functor between categories with finite products, and you want to say that it preserves products. You don't say there are maps that satisfy some coherence conditions. You say there is a canonical map, always. And then you say that canonical map has to be invertible. Full stop. You don't ask coherences for a product-preserving functor. And then you prove that, for example, it's a monoidal functor. Okay? So this is our way, at least at the moment, for addressing the coherence conditions. So this is the theory of differential categories in the two-dimensional setting. In the 1D, there are a couple of references there. Okay. So I want to finish by presenting an example of such a thing. And that's the theory of analytic functors or generalized analytic functors. So everything I'll do is based on this bicategory of profunctors, that is our 2D version of relations. And just like relations, bicategory of profunctors has lots of structure. It's symmetric monoidal with tensor given by the product of categories. It has biproducts given by disjoint union of categories. It's compact closed given by taking the opposite. And if you write out what the internal home, you get also a formula for it. So it's completely analogous to relations. And just like the free commutative monoid monad on set extends to relations by a form of distributive law, and then can be turned into a comonad, similarly, the free symmetric strict monoidal category 2 monad on cat extends to a linear exponential pseudo comonad on prof, in the sense that we discussed before. So what is the free symmetric strict monoidal category on a small category A? Well, it's a category that has as objects finite sequences of objects of A, and a map between two such sequences is a bijection between the numbers of elements in the sequences, which can exist only if the two sequences have the same length, and then a family of morphisms Fi from one to the other, shifted by the permutation in A. Okay, so it's some kind, instead of quotienting by these symmetries, as you would do to get the symmetric, the commutative monoid on a set, we keep track of the symmetries. Okay. And now going towards analytic functors, I define a categorical symmetric sequence simply to be a Kleisli map for this pseudo-comonad. Symmetric sequence from A to B is a profunctor from, of course, A to B. And just like profunctors are my linear maps, these symmetric sequences are my non-linear maps. And this idea can be made even more explicit, defining what is called the analytic functor associated to a symmetric sequence. It's a functor from presheaves on A to presheaves on B, which take a presheaf on X to a certain coend, whose coefficients are given by the values of, I should have written M here, times x to the alpha, where x to the alpha is just the product of x, a1 to x an. And this is a bit reminiscent of the formula for exponential power series. And indeed, it's a generalization of Joyal's notion of an analytic functor, which is even more connected to that formula, which is when occurs when A and B are just one. Okay. So what's the idea? That the analytic functors on set are a bit like the analytic functions from R to R, and this analytic functor from presheaves on A to presheaves on B are a bit like analytic functions from Rn to Rm. And our goal is to extend the differential calculus of analytic functors in one variable to analytic functors in many variables. And of course it works, but it works because this linear exponential pseudo comonad admits a co-dereliction operation, d bar, and therefore one has the whole setup of the differential categories in just in 2D as developed by many authors. So what's my co-dereliction? And I'll finish in a second. It has to be a profunctor from A to, of course, A. So it has to be a functor from, of course, A up times A to Z. And what does it do? It takes a sequence, an element, an object of A, and just returns the hom set in, of course, A between the sequence and the singleton. And now we can calculate the derivative of a Kleisli map or the derivative of an analytic functor. And that's what you get. So let's start with a Kleisli map from, of course, A to B. Its derivative, if you unfold all the relevant definitions, is a profunctor from A tensor, of course, A to B. So it has to take B in a contravariant position, and then an A and an alpha in a covariant position. And it's simply defined to be the value of F on B and the concatenation of alpha with the singleton sequence A. Okay, so this guy is not quite ready to live in a Kleisli bicategory. Because there is this A, so I need to move this A on the other side. That's what this step is doing. And now we're game, because now we have something from, of course, A to something else. And we can take the analytic functor of that, and you get this formula, where you're just moving the coefficients by 1. Exactly like it reduces again to Joyal's formula for analytic functors on set, which in turn is inspired or corresponds to the derivation of exponential power series, which occurs just by shifting by 1 the coefficients. And this shift is precisely this extension of the list by 1. So that's the upshot of what we did. Now the calculus of differential calculus of analytic functors, including the chain rule, product rule, they all follow from these axioms. Okay. So last thing to say, and then I really wrap up, is that I've been very fond of this bicategory of polynomials and polynomial functors. But here's another bicategory that is a lot of fun to work with and has a lot of structure. It's this Kleisli bicategory of analytic functors or generalized analytic functors. It's Cartesian closed. It has this derivative operation. In joint work, this is all joint work with various combinations with Fiore, Hyland, and Winskell. It has also an arithmetic tensor product, which gives rise to an Oplux monoidal structure. This is work with Richard Gardner and Christina Vassilakopoulou. And it also has fixed points operators. That's work of Zainab Galal. So it's a very rich playground. And for those of you who are fond of polynomial functors, I invite you to play around also with the generalized analytic functors. And I'll stop here. And thank you.
Thank you. Hey, okay, we can open it up for questions. People can either raise their hand or just unmute themselves. I think we have Kevin has a question, so go ahead, Kevin.
Sure. Thanks a lot, Nicola. Really, really intriguing talk. Let me ask first, these generalized analytic functors between pre-sheaf categories that you're finding, do you have a characterization of those? I think the unary Joyal analytic functors preserve like filtered co-limits, co-filtered limits, weak pullback.
Very good question. There's a theorem due to Marcello Fiore that when, let's go back, where are we? Yeah. When A and B are groupoids, it's possible to give a characterization. When A and B are arbitrary categories, we don't know. So it's a
Interesting.
paper
Yeah.
of Marcello from a few years ago. Yeah.
Interesting. Thank you.
Thanks, Kevin. And Valeria has her hand up. Go ahead, Valeria.
Hi, Nicola. That was beautiful. Really very beautiful. I'm kind of
Thank you.
very excited about the whole thing. But I kind of wanted you to go back to slide 15, if you don't mind, because I don't even know if I have really a question, but I think I do. I think, I mean, trying to summarize for myself what is happening here is that, you're showing that the stratification that we need to do to simplify the categorical models is much harder than people thought initially, right? And that's I think what's happening with the business of some isomorphisms becoming identities, some not, and taking all this syllabtic things and stuff like that. But so this is good. This is fun. This is very good to have a goal in mind. Kind of take the logic and try to find categorical ways of making some equalities that the logicians don't. I mean, the logicians, because they're only thinking about implications, don't see the difference between kind of between things that are really isomorphisms and things that are just natural transformations or something. So the question I have really is whether that already proved the fact that that if one's thinking about linear exponential comonads or monads, so kind of trying to think of these things as modalities in modal logic, if it means that we actually should, I mean, that we need to go to this step of being careful with the equalities. So, people tend to say, let's just assume that the comonad is idempotent and kind of try to simplify like that. I think what the work that you're doing here is showing is that that's not good enough, that you actually have to look deep to see. But I don't, I'm very confused, but I think it's kind of clarifying lots of stuff. But there's more clarification that I need still.
Maybe the one thing that maybe would be interesting to look from the logic side of things is around this cut elimination.
Yeah.
So I think people in logic are just happy to have a cut elimination theorem.
Yeah.
Every sequence, every derivation can be transformed into a cut-free one.
Yeah.
But one could have more than one cut elimination procedure. And there's a question of comparing them.
And
I think that's what this, maybe some are more efficient, maybe some are more canonical than others. So in the context of type theory, it's the fact it corresponds to, cut elimination corresponds to making a term into normal form. But here we're looking for something extra. We're looking at different ways for making a term into normal form. And in that context, there are theorems, which I don't claim to understand the proof of, which are called standardization theorems, that tell if I can reduce a term to normal form, I can always do it in a standard way, performing the reductions in a certain way. And maybe it has something to do with the fact that maybe one can canonically apply the coherence axioms in a certain way. So maybe that's, yeah, I don't know.
Now that
Maybe it could help with
good.
some automated aspects of proof checking. Yeah, I don't know. Speculation.
Very good. No, thank you so much. I think that at least gives me ways of thinking about it. Thank you.
Okay. Thanks, Valeria. So we don't really have much more time for questions. I had a brief one, and then maybe Kevin seems to have another. I'm not sure. If I understood right, you're looking at the category you're interested in, Prof. Bang, is so the objects are categories, and a morphism from A to B is a map from the free symmetric monoidal category on A, a profunctor from that to B.
Yeah.
And so I was wondering, so monads, if I didn't have the Fleisley stuff, the monads in there would be pro-monoidal categories?
Yeah.
Do you know what monoids? Do you know what monoids would be? Do you have any examples of a monoid in this thing?
A monoid in Prof. Bang?
Yeah, is that an interesting question?
Yeah, it's a colored operad.
It's a colored operad. There we go.
Well,
Okay.
with an underlying category of colors.
Interesting. Okay, thank you.
So you can take also the discrete A, B, C, and then, yeah.
Yeah. Okay. It would have a symmetry.
Yeah. So.
Okay.
Sorry.
Well, I think I'll ask you any more on that offline. But can you have a very brief question?
Yeah, it's probably just a yes or no answer. The formalism for Bang you picked are these pseudocomonads that are what Lex symmetric monoidal. Do you know whether that's as strict as I'm allowed to get in looking at, like, can I not get a two comonad on a symmetric monoidal bicategory that continues to have the monoidal structure?
So for pseudocomonads, well, you can make the endofunctor strict. To what extent the monoidal structure can be strictified, I don't know. I don't know if there are coherence theorem for lax monoidal two functors or things of the sort. Yeah. Good question. Yeah.
Okay, let's stop here. Thanks again, Nicola.
Thank you.
Stop the recording.